Alright, this is Precalculus section 3.1, linear functions and their properties. Yay, back to linear functions. Remember when we did this in Algebra 1 and we're like, what? Y equals mx plus b? It's terrible. So the first section is graphing linear functions. There's our wonderful slope-intercept form, f of x equals mx plus b, where m is the slope and b is the y-intercept. Okay, so if we had a function f of x equals 2/3 x plus 1, we match up the m value, the slope, with the y-intercept, which is, the slope is 2/3 and the y-intercept is 1. 0, 1. So we throw down the y-intercept at 0, 1. Then we apply the slope. So slope is the change in y over the change in x. We talked about that last week. Delta just means change. Instead of writing C-H-A-N-G-E, we write a little triangle. So we go up 2 over 3. And we have our next point. Then we, easy peasy, just draw a line. Right. That's all of that. We've done that enough. We don't need extra craziness on that. We're going to take that to the next level by using the average rate of change to identify linear functions. So if we have a function and we go from, we plug in values, and we find the change in y over the change in x. So here I'm going, change in y goes from 13 to 10. Change in x goes from -2 to 1. Sorry, -1. And my average rate of change is -3 from this point to this point. So from this coordinate to this coordinate, we do the same thing. We got 7 minus 10, change in y. 0 minus -1 is a change in x, and we see that it is also -3. So linear functions have a constant average rate of change. That is, the average rate of change, f of x equals mx plus b, is delta y over delta x equals the slope. So that's what actually makes it linear, is its rate of change is constant. It drives and makes that nice straight line, because you're always going up the same amount and over the same amount. All right, so let's use it to tell whether functions are linear or not. Oh my goodness. So a strain of E. coli do 397 RECA441 is placed in a petri dish at 30 degrees Celsius and allowed to grow. The data shown in Table 2 are collected, the population is measured in grams, and the time in hours. Plot the ordered pair in the Cartesian plane and use the average rate of change to determine whether the function is linear. So the first thing we're going to do is plot these points. And we here, and just as population normally does, it increases in a nice curved shape. It's just the way, the nature of populations. So taking that and then using the average rate of change from coordinate to coordinate, so from 0 to 1, our average rate of change is 0.03. From 0 to 2, so if we go here, the average rate of change is 0.04. From 2 to 3, it's 0.06. From 3 to 4, it's 0.07. So our rate of change is increasing. So it is not constant, which makes it not linear. All right, let's see another example. In data table 3, the data in table 3 represents a maximum number of heartbeats that a healthy individual should have during a 15-second interval of time while exercising for different ages. Plot the ordered pairs and use the average rate of change to determine whether the function is linear. So we're going to do the same thing we did before. We're going to plot these points And this one definitely looks like a nicer, straighter line than the population growth. So, but we're going to use the average rate of change to see if it's actually the same. So when you do the calculation, change in y over change in x, we get negative 0.25. You apply that calculation between each of our coordinates, and you get the average rate of change is negative 0.25, constant for all of our data points. So we can say that the function is linear. Constant, average rate of change, linear function. All right, determining whether a linear function is increasing, decreasing, or constant. This is going to be easy peasy, because if the slope is positive, it's increasing. If the slope is negative, it's decreasing. And if the slope is constant or zero, then, or if the slope is zero, it's constant. So positive is increasing, negative is decreasing, zero slope is constant. So let's see what that looks like. We're going to look at 4 linear functions and see if they're increasing, decreasing, or constant. This should be, you should be able to glance at these and immediately fire away. A is decreasing. B is constant because the slope is 0. C is increasing because you have a positive slope. And D is increasing because the slope is 1. So this should go, the reason we learned all this stuff in Algebra 1 is so that we could make these identifications fast. All right, so now here's the hard stuff. Building models with verbal descriptions. So the average rate of change of a function is the constant m. A linear function f can be used to model a relationship between 2 variables as follows. F of x equals mx plus b, where b is the value of f at 0, and b equals f of 0. All right, so here it is. Book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation, so that the value of the asset declines by a fixed amount each year. The amount of decline depends on the useful life that the company places on the asset. Suppose that a company just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each value using the straight line method over 7 years. This means each car will depreciate $28,000 divided by 7, $4,000 per year. Write a linear function that expresses the book value v of each car as a function of its age. So we're going to say v of x, value for v, is the value of each car after x years. We're going to say that its initial value is $28,000. The slope is negative 4,000, since it depreciates that amount each year. So my function is negative 4,000x plus 28,000. So we're going to graph this linear function. We start at 28,000, and our change in y is every year we lose $4,000. So what is the book value of each car after 3 years? We just need to plug in 3 and find that it's $16,000. Interpret the slope. Oh yeah, it's the average rate of change. It means that each car loses $4,000 per year. When will the book value of each car be $8,000? We look over at our graph. 8,000 happens, looks like year 5, but we can solve our equation for that. And it is, when we solve for x, we plug in 8,000 for y and solve for x and we get 5.